Okay, let's begin with a word of prayer. Dear Heavenly Father, we thank you again for this opportunity we have to meet together and study your creation. Just pray that you'd help the students to understand the material we go over today and help us, Lord, to glorify you in what we do here. In your name I pray, Lord Jesus. Amen. Okay, so two little tidbits about the test, and then I'll get back into the material. So there's a half of a solution about the cancellation problem. So you're given A is not equal to 0, and I also gave you the data that A dot B is equal to A dot C, and A cross B is equal to A cross C. So it was given that there exists an A such that this is true, right? Now, if it was true for all A, then we'd be done. We'd know that that implies B is equal to C. In fact, this also implies B is equal to C. This is enough information to get it. Let me show you how. So the solution, well, I mean, there's probably a couple dozen different ways to solve this, but here's a way. So by properties of the dot product, by properties of the cross product, you can rewrite the given conditions as follows. So the A is perpendicular to B minus C, and apparently A is also parallel to B minus C, or collinear. And if you have a clear mind geometrically in 3 dimensions, you realize already that the only thing that's parallel and perpendicular at the same time to a non-zero vector is the 0 vector. So it's immediately clear that B minus C is equal to 0. If you feel a little empty inside when I tell you these words, you're not alone. I mean, that's one proof. But I kind of prefer what I'm about to show you because I think it's less geometric, but perhaps it's more algebraic. Some of you will like the algebraic solution more. So, of course, we have proved that this is the same as A times the length of B minus C. So A without the vector is the magnitude, right? And then you can look at the cosine of the angle between, right? You can look at here's A, and here's B minus C. I'm calling theta the angle between them. Okay. And then let's see this equation. What did we find about the modulus? The length of the cross product. Well, it's A times it's the length of each of the things being crossed, right? Times the sine theta. So that's equal to 0. And this is equal to 0, right? But what do we know about A? A is not equal to 0, right? Since it's not the 0 vector, right? The only thing with 0 length is the 0 vector. So what does that say then? You can divide both sides by A. And what conditions do we get? We get that the length of B minus C times cosine theta is equal to 0. And the length of B minus C times the sine of theta is equal to 0, right? Here's a fun fact about sine and cosine for you. Sine squared plus cosine squared theta is equal to 1. What does this happen to say about sine and cosine? Are never both 0. So, go back to these equations. If sine and cosine are not both 0, at least one of those is non-zero. Consequently, the magnitude of B minus C must be 0. But if the magnitude of B minus C is 0, that implies that B is equal to C. I think that this solution was within your grasp, if you thought about it. Nothing I'm saying here is dramatically new news to you, I hope. Yeah? I mean, you should have known about this. You should have known about that, right? You should certainly approach my test questions with the attitude I can solve this. The question, have I done this before, is, that's okay, that's fine, that's part of taking a test, but there are always going to be a couple questions on my test you haven't done before, because it's a university course and I have to test the concepts as well as your practice. But anyway, so that's that. Any questions? All right, let me talk about problem number 4 then, with the unfortunate grammar and the even more unfortunate given data. If you'll excuse me, I must do something. So suppose you're given that A cross x hat is equal to minus z hat. You're given that A cross y hat is equal to 2z hat. And you're given that A cross z hat is equal to minus 2y hat plus x hat. Now, I think if I had set up the problem this way, it would have been a reasonable problem. The thing is, I just made up the things that they were equal to, and you can't just do that. It's not possible just to arbitrarily assign the outputs of the cross product of a vector with x hat, y hat, and z hat. It overdetermines the system in an inconsistent way in general if you don't choose wisely. I mean, I knew enough to make A cross x hat not depend on x hat, right? I knew enough to make A cross y hat not depend on y hat when I was making the problem, right? I knew that. But it didn't dawn on me until I was solving the problem. I can't do that. This one will work, though. So if I want to calculate the cross product then of A with 1, 2, 3, and you see this is what I'm a little bit concerned about is it doesn't look like any of you there were very few of you who were really in the hunt for this problem. And it's not that complicated because all you have to do is use what's given in properties of the cross product. You ought to be able to do it. See, this is what? This is A hat cross x hat plus 2y hat plus what? 3z hat, right? So you know that the cross product's distributive, so you just distribute A cross x hat plus 2 A cross y hat, right? Plus 3, what was it? A cross z hat. And then, well, I gave you those, right? The problem with the problem on the test is what I gave you was impossible. So that's 4z hat. And A cross z hat would be 3 times, minus 2y hat plus x hat. All right, so if I rewrite that in the bracket notation, I get what? I get 3 minus 6. And what is it? And 3. All right. So once I did that on my solution, I knew I was wrong. Because I looked at it, and I took the dot product with 1, 2, 3, and I didn't get 0. So I knew the problem didn't make sense at that point. That's why I said that to you guys. But I was hoping some of you would just do this, basically, the analog to that on the test, and just not notice that it's dot product with 0, because as much as I tell you guys to check the dot product to make sure it's 0, many of you don't actually do that, right? Maybe most of you do it. I think something like 90% of you had the cross product right. Yay. That is a good thing. That is somewhat atypical. There's usually about 20-30% of you guys who can't do the cross product reliably on the test, first test. Cross product's a pain, though, right? Okay, so is this perpendicular? 3 minus 6. Ah, man. What'd I do? Oh, it's minus 12. I can't multiply. So, yeah, 3 plus 9 is 12. 12 minus 12 is 0. Good. Okay. Now, what was the A here? What is the vector A in this case? I didn't ask that, but it's kind of an interesting question, right? How would you figure out A given all this data?
1, 2, 3 cross that.
It's what?
1, 2, 3 cross that. You either end up with A or the negative of A.
1, 2, 3 cross that, but that will just give me, oh.
Well, if you're going in the right direction, but
Ah.
What you're saying, magnitude, that's the difference.
Yeah. I think there's that identity about the cross product of the cross product that we derived in the homework. You could use that. That would be probably the fastest way. The other way that occurs to me right off the top of my head is just to take, like, think about A symbolically for a second. So let's let A be ABC for lack of imagination. So if I take the dot product of this equation, right, with, if I take the dot product of this with what? A cross x hat dotted with z hat, what's that give me? So you can work out what is A cross x hat. What is A cross x hat? Yeah, it has a B and a C in it. It's B what, though? What's the only thing that matters here? What's the only thing that contributes to the Z component? What'd you say? The B term, right? I think you already told me. So it would actually be minus B, right? Well, fine. I could say this is B y hat cross x hat dotted with z. The other terms I'm dropping are negligible, right? Because you've got terms that either dot product with z to 0. Everything else dot products with z to 0, right? Or it's just 0 because the cross product doesn't, the cross product with x hat doesn't have an a term in it. So that's minus z, so I get minus b. And this is, but it's also equal to what? Take the dot product of this with z hat gives you what? So this is equal to minus 1, so therefore b is equal to 1. See, I took this first equation, the dot product on both sides with z hat, and it gave me b is equal to 1. And then I can do the same thing with the other equations, like let's see here, let's do this one. If I take the dot product with y hat, with z hat here, what would that give me? That equals 2, right? But what does that tell me, though? What's the only thing that matters? What can give me a z component crossing with y hat? Just the x hat, right? So this is just a x hat cross y hat dotted with z hat. And so that's a. A is equal to 2. Yeah.
Sorry, I think I missed the connection. How is it that we know that AX hat is the only relevant part of A?
Well, think about no, but think about taking the cross product of A in such a way that you can create something with a z component, right? The only thing that survives dot product with z hat is a z component. So the things that go into making the z component are either what? X cross y or y cross x, right? But it can only be x because the y hat is fixed here, so you can only get x hat, the x hat part of A. The y component of B cross products to 0 as you take the cross product with y hat. So that's gone in that this calculation right here. It doesn't pick up anything about B. And then if you take a dot product of the third equation with respect to what? Well, that's the thing, is this one, you can take the dot product with respect to x hat. What do you get? On this side, you get, a cross z hat dot x hat, and that's equal to 1, because x hat dot x hat is 1 and x hat dot y hat is 0. Now a cross x hat, the only thing that gives me that has to be the b component, right? So again, I get b y hat cross z hat equals to 1, but y hat cross z hat dot x hat is equal to 1, but this is precisely x hat, and so there we get it again, b is equal to 1. So you get b equals to 1 independently from the third and the first, and so I can't just choose these two independently. They're wrapped together because of the structure here. They're intertwined. But anyway, I didn't actually ask you to find a, so that would be that's a harder question, right? Any questions?
Were you going to try to find C on that, or are you saying that that won't be found? And the answer could be no, you weren't, but I'm just curious.
Let's see here. Where would C appear? Huh. I guess if there was a C term, right, that should have appeared here. So, I mean, these implicitly say C is equal to 0. If there was a C term, right, then if there was a C term, for example, this one, I would have had C z hat cross y hat, right? And that would have given me what? Z cross y hat is minus cx hat, right? But as you look at the other side, there's no x hat, right? So the only way that can be is if C is 0. But that's a good question. I stopped there because I made this up by writing down x hat plus, 2x hat plus y hat, and then I took the cross product with x, y, and z to make this example, which is what I should have done on your test. But you should be glad I didn't do that, because I effectively didn't grade this problem, which is fortunate for you guys, because I don't think there are many of you who would have gotten this right this time around. Don't think. It didn't appear to me. Well, there were about 5 of you who looked like you might have gotten it right. If just slightly worked it different, but. Okay, anyway, any questions about anything else? So solutions on Blackboard, I wrote you a monstrous announcement that you can look at. I'm 13 words shy of 1,500 words on that thing. Sorry about that. You know, brevity is the soul of wit, so you can figure that out. The audio is working, isn't it? Okay, good. Don't worry, though, if you don't quite understand vectors yet, we've got a whole semester of it ahead of us. So they will catch on sometime soon. All right, so last time I gave you some false advertising. I told you I could tell you everything that there was to say about limits in that talk. That's not entirely true. I still have some more to tell you. So, but the good news is, last time we were very, I don't know, it's kind of unnerving, the whole idea of last time. I was basically selling you this idea, if you suspect that the limit doesn't exist, then you look at 2 different paths and show that they don't match, and then that shows that the limit doesn't exist, right? And it kind of begged the question, well, which 2 paths? And I didn't really answer that. And if you were to ask me, I would tell you, well, what I usually do is I start with, if I think it doesn't exist, I'll start with coordinate axes, because those are easy. If that doesn't work, I'll try every possible line, like the t comma mt we did. If that doesn't work, then I'll go to parabolas. That's not really true. I almost never get to parabolas. But that's kind of, I kind of showed you the standard bag of tricks last time as far as that goes. But there's one other tool in our toolbox which is really very nice, and that's the method of coordinate change. Coordinate change is really, really helpful. Because it doesn't just give you the negative answer that limits don't exist. Sometimes you can use a coordinate change to show a limit does exist, because sometimes some of these functions, once you do the coordinate change, it will actually change it to an expression which is amenable to first semester calculus. And so, that's a win. We can actually show some of these converge in this way. So here's an example. So suppose we have 2xy over x squared plus y squared. for x, y not equal to 0 and x, and it's just 0 at 0, okay? So here's the idea. Change the polar coordinates. All right, so we want to calculate the limit as r goes to 0 of f of r. So I argue that this is equivalent to taking the limit as the radius goes to 0 of f of r cosine theta, r sine theta. In other words, just set x and y equal to their coordinate, polar coordinate substitutions, right? So limit as r goes to 0 of 2, I get r squared, right? Sine theta cosine theta upstairs. And downstairs, I get myself an r squared cosine squared theta plus r squared sine squared theta. So what's that? Yeah, the sine squared plus cosine squared. It's always sine squared plus cosine. Everything we do is sine squared plus cosine squared. I'm sorry, it's so boring. I'll try to put some hyperbolic examples in the test or something. I'm just kidding. I don't really have any of those. I should make up some. I don't know. Hyperbolic coordinates are kind of fussy. I'm not sure I believe in them. Okay, so that's just r squared. And there's an r squared upstairs, right? So they cancel. And you're just left with 2 sine theta cosine theta, right? And I don't know. Fine. If you want, we could rewrite that as what? That's really just sine of 2 theta, right? One of those things you remember from trigonometry. You should be aware of this identity. And so what happens as r goes to 0? Yeah, there's no r. So just think about it, right? If you approach the origin from different angles, you get different values for the sine, right? So this limit doesn't exist. Different rays produce different values for sine of 2 theta. I was trying to tell you these substitutions as if they actually give you actual answers to limits. This is not that example. This one would also be, you could also solve this with the two-path test, right? You could look at, if you wanted to solve this with the two-path test, just an outline, you could show the limit of, say, 0 comma t going to 0 of f, f of xy. You could show that that was equal to 0. And on the flip side, if you look at the limit of tt going to 0, 0, if you do that path limit, I can just see from looking at it that you're going to get 1. I know that the coordinate path is 0 because the numerator is x times y. So the fact that y is 0 makes the expression strictly 0 as t goes to 0, right? But on the flip side, if you look at the line y equals x, which is parameterized by t comma t, you feed that in, you get 2t squared over 2t squared, which is 1. So the path limit would work out to 1, right? But the cool thing about the polar coordinate substitution, right, is I don't have to do this. I can think in terms of polar angle. And I do get some kind of better geometric sense of what's going on, right? And you can even see these path limits in here. What would this be? Zero t going to 0 is what? That's this one, right? Oh, I'm an idiot. Duh. It's obviously the y-axis, right? X equal to 0. Stooge. So that's that one, right? That's theta equal to what? Huh. Wait a second. Oh, no, that makes sense. What's 2 times 90? 180? Sine of 180? 0, right? What's the other path? This one, right? Which is what, 45 degrees? Sine of 90? 1. But the cool thing about the polar coordinate substitution is it doesn't, I mean, it kind of, it's another kind of sneaky way of looking at all paths in some sense. Let me show you another example. I'm going to skip example 4 in my notes. I'm going to go over here to example 5 because it's more fun. I want to look at the limit as xy goes to 0, 0 of x squared plus y squared divided by x to the 4th plus 2x squared y squared plus y to the 4th. So my intuition is that this diverges because it's got quartic power in the denominator, only quadratic in the numerator. But I can give you a pretty strong plausibility argument for it using change of coordinates, right? So limit as r goes to 0, and let's see, that's what, r squared? And this is what? Let me just point this out. This is what? This is actually x squared plus y squared squared, isn't it? So this, in fact, is r to the 4th. I mean, if you guys don't like these, we could do more epsilon deltas. Just kidding. I hope you enjoy these more, yeah? I'm sorry, it's too soon. I forget the test just happened. It's too early in the morning. All right, here's another one. Again, polar substitution is a pretty good option here. I don't know, you might be able to do this with squeeze theorem. Maybe not. Limit as r goes to 0 of what? Sine of r squared divided by r squared. So what do you do here? It's still indeterminate, right? Top's going to 0, bottom's going to 0, but this is a calculus 1 problem. Right? Type 0 over 0, we can use L'Hopital's, yeah. So L'Hopital's rule, type 0 over 0, I differentiate the top, I differentiate the bottom. And what do I get? I get 2r cosine of r squared divided by 2r. The 2r's cancel. And I'm left with the cosine of 0, otherwise known as 1. There you go. Now, to the pure of heart, there's really no need for L'Hopital's rule here, because what you're looking at is sine of a quantity over the same quantity as the quantity goes to 0. This is a fundamental limit that's known to be 1. But if you forgot that, you can easily derive it with L'Hopital's rule, which is technically circular because L'Hopital's rule assumes the existence of sine x over x being 1 as x goes to 0, but it's okay. That's proved with a circle anyway, so it's all circular. Sorry, I should shut up. Let me show you a picture of this thing. It's kind of fun. Behave. So we're just about ready to start partial differentiation, all right? Oh. So I wanted to get out the projector to show you some pictures about that too, so because I have some pictures in my notes that are just better than what I'll do by hand here. Come on. So here's actually a picture. Here's a graph. This is what z equals to, x squared plus y squared divided by x squared plus y squared looks like, where we define the function to be 1 at the origin. Basically fill in the hole there. Isn't that cool? I don't know. I think it's cool. If you graphed it further, it kind of keeps rippling. Smaller and smaller and smaller waves as you go off to infinity. Right? Because sine is always stuck between plus or minus 1, but you're dividing by something that's larger and larger and larger. So it horizontally, as you get further and further away from the origin, it tends to the xy plane. So now, I should mention you can do the same sort of thing we're doing in 2 dimensions for 3-dimensional limits. Like if you face something like this, if you make a spherical substitution, that helps. If I change this to spherical coordinates, this is like rho, natural log of rho squared. And then again, you can play the same game to do those kinds of limits. So I hope you see that one works out to 0. That's pretty much it in terms of limit techniques I have for you. We have the definition, squeeze theorem, limit laws, right? And then this coordinate change idea. That's pretty much it. Any questions? Actually, there's one other token problem. We usually give you something like, here's a case-wise defined function, and there's a variable constant in it. Choose the variable constant such that it makes the function continuous, right? So how do you solve those kinds of problems? Same way you did back in Calculus 1, right? You assume continuity, and then that will force a condition on the constant. So we can talk about that some other day if you guys can't figure out the homework problem. I think I asked one about that, but I'm going to go on to partial differentiation because it's far more interesting. All right? So that brings us to, problem 75 is an example of what I was just talking about. Choose a value for a such that this is continuous. Okay. So if you look at the solution to problem 75, there's an example. And that brings us to the problem of differentiation at last. Now, there's slightly more sophistication in my notes on differentiation than you usually see in the standard books. I'll actually talk about these partial derivatives we'll soon define in terms of some larger notion of what differentiation is. So the basic idea behind differentiation is simply this, though. If you've got some function from one space to another, the derivative of that function is some sort of object which allows you to find the best linear approximation to the change in the function near the point. All right? So the first thing we talk about in that vein is what's known as a directional derivative. So the idea of a directional derivative is this. You look at some function of 2 variables. Let's start with 2 variables. Then you can look at its graph, z equals f of xy, right? And so the graph maybe looks, it's some kind of curved thing. And then the idea is then to pick a particular point, say x naught, y naught. I know it's kind of blurry here, but picture some particular point in the domain, and we want to study how does the function change at that point, right? But the thing is, is there's lots of different directions, right? So we focus our efforts on seeing how the function changes at that point in the v direction. So, or the u direction actually here, a unit vector. And I use a unit vector u hat. So we're at this point, and we're studying the, how does the function behave along this direction in the domain? So that gives me some curve on the graph, all right? That's actually the same kind of calculation I was just talking about over there for the limit. We're looking at the function composed with a particular path, and we're studying how the function changes as you feed it values from that line in the domain. A line with direction vector u hat at that point. And so if you just set aside the three-dimensional picture and then just focus on that vertical plane, you've got this trace from the graph, right? And then you've got some tangent vector to that curve, right? And that the tangent vector to that curve will describe how z is changing with respect to time. The slope of that will give you the instantaneous rate of change of the function in the u hat direction at the point P, right? Now you can talk about the rate of change of the function in not just one direction, but all possible directions, right? Because as you're looking at a three-dimensional graph, you can sweep around all those different directions, right? So you can talk about directional derivative 360 degrees. And so let me define it now that I've hopefully motivated the general idea here for you. So to be precise, let me get rid of this silly thing. Enable scrolling, yes please, I would like that. No! What does scrolling mean to you, Adobe? It scrolls until it doesn't scroll. It's like it just jumps into the next page all of a sudden. Anyway, so what I was trying to motivate there for you is that if we look at the function, basically, f of xy, and then we plug into it a line in the domain with base point x naught comma y naught and direction vector ab. So a comma b is like the u hat I had in the previous picture. Then what this is this is the value of the function along that line in the domain, right? So if I differentiate that with respect to the parameter of the line, and then I plug in time equal to 0, that gives me the instantaneous rate of change of the function along the line. That's what we call the directional derivative. Here's the careful definition. Then here's notation for it. The directional derivative of f in the u hat direction at the point p naught is given by this limit. So what this is doing is it's just adding a multiple of the u hat vector, and it's fixing everything else. So you're just changing the argument along the u hat direction, but no other direction, right? And you're taking that change to 0. That's the directional derivative. Now, here's it in more detail. If a and b are the components of u hat, then you do x naught plus ta, y naught plus tb, minus f of x naught y naught over t. That's the definition of the directional derivative. Okay? But pragmatically speaking, this is a nice formula for it. You just take your function, you evaluate at the appropriate line and differentiate. Once the differentiation is done, you put t equal to 0, right? So that's actually not how we typically calculate, so let me just talk through it with you here rather than actually working it out. So this example, I have the function 25 times xy, right? And I want to calculate the rate of change in the 1, 2, at 1, 2 in the direction of the 3, 4 vector. Just to give you an example of how the definition works out. So first of all, I have to take the 3, 4 vector and normalize it. I need a unit vector. That's part of the definition. So the unit vector, I have to divide by 5 because 3, 4 has length 5. So I get u hat 3 fifths comma 4 fifths. And then I look at f along the line based at p naught with direction u hat. And that gives me 1 plus 3t over 5 comma 2 plus 4t over 5. And then I plug this into the formula for x and y. It gives me 25 times this stuff, which gives me this lovely formula. And then I differentiate. Differentiating gives me 30 plus 20 once I plug in times 0. So there you go. The directional derivative of this function in the 3, 4 direction at the point 1, 2 is 50. My next example. Same function, all right, but this time I study the directional derivative in the x hat and the y hat direction, all right? So almost the same idea. I calculate the directional derivative in the x hat direction, I get 50. I calculate the directional derivative in the y hat direction, I get 25 actually. We differentiate this, it gives you 25, okay? So then you can compare the 50 we got in the previous example to the 25 we got in this in the following way. It's 3/5 times 50 plus 4/5 times 25. Just to be more, I'm showing you the pattern here. Where'd it go? Stupid thing. There it is. So my first example, I had AB. I had U hat, which was 3, 4. And then I figured out, which was actually 3. You remember U hat is what? Sorry. 3/4. Oh man, no, 3/5. I was really confused all of a sudden here. Yeah, 3/5, and then what was it? 4/5, right? Okay. That was U hat. 3/5, comma 4/5. So you notice what's going on here is you've got those same components here and here, right? And then multiplied by the rate of change in the x hat direction and the rate of change in the y hat direction. In other words, you could see this pattern. The directional derivative in the AB direction, it's a comma b dot the directional derivative in the x hat direction, and then the directional derivative in the y hat direction. Right? So there's something special about the directional derivatives in the x hat and y hat directions, is my point. This turns out to not be an accident. This is actually a general theorem. You can calculate the directional derivative by using these things, which we will be calling partial derivative with respect to x and partial derivative with respect to y. Here's a picture. Here's a picture. Where'd the picture go? Picture's in the next section. So the definition then is the partial derivative of f with respect to x is the directional derivative in the x hat direction. The partial derivative of y with respect to partial derivative of f with respect to y is the directional derivative in the y hat direction at the point. All right, provided they exist, of course. So just before I forget, my So with the thing we just wrote, which was that the directional derivative in the AB direction, right, of f at the point P was equal to a comma b dotted with what? The directional derivative in the x hat direction of f at P, directional derivative in the y hat direction of f at P. What is this actually? This is a comma b dot with partial f, partial x at P, partial f, partial y at P. Those are not it's not d, it's partial. This is a new symbol, okay? It's not a 2, it's this, partial. So apparently we can build the directional derivative in the AB direction using just the partial derivative with respect to x and the partial derivative with respect to y. And you just take the dot product. Here's some notation for partial differentiation. We use an f sub x for partial x is a shorthand. F sub y is a shorthand for partial f partial y. You can also talk about second derivatives. Partial squared f partial. That just means you differentiate the derivative function again and so forth. So it's important, though, that we cement in our mind the meaning of f sub x and f sub y. F sub x, or the partial derivative of f with respect to x, What does this do? It gives us the rate of change of f in the x direction. F sub y gives us the rate of change of f in the y direction, all right? And it turns out that the rate of change of f in any other direction can be built from these two fundamental rates, provided the function is not pathological, right? If the function's sick, who knows what could happen. But we will study continuously differentiable functions which are well behaved. They'll never win any awards. All right. They don't have the proper shock value, you know. And again, here's you know, if you distill the definition of the directional derivative down to its, you know, this is just the definition in another notation again. To calculate partial f partial x, what I do is I take the y component of the function and I just freeze it. The y component is fixed at y naught, and then the x component is allowed to vary. You differentiate with respect to x, holding y fixed is what this says, and at the end of it, you put t equal to 0. Like now over here, the x naught is held fixed, and the y component's allowed to vary. At the end of all that, that's what the partial derivative is. I mean, it's just y varies while x is held fixed. X varies while y is held fixed. I mean, these are partial derivatives. Now, geometrically, what's going on is this. All right. So if I think about the graph of a function and I want to understand geometrically what is partial f, what is partial x, what is partial f, partial y, what do those mean geometrically? They're the slope of the tangents to the point in the graph, which are found if you look at these particular vertical cross sections, right? Either holding what? This cross section does what? It holds y fixed, right? And x is allowed to vary. So the slope of this has to do with the x derivative, the partial f partial x. This other plane, this other vertical plane, holds x fixed while y varies along the green curve versus along the, I can't see the color. maybe it's orange, I'm not sure, I can't tell. But here I've drawn it over here for you again. You can, you know, both of those vertical planes you can think of in a two-dimensional sense, and you can just think about the slope like we did in Calculus 1 of the function, either holding x fixed or holding y fixed at the point. Any questions about this? So what is the x derivative? What does partial f partial x mean? What's the slogan for it? What?
Rate of change of the function in the x direction.
Rate of change of function in the x direction. Yes. I think that's fair. Anybody else care to add another slogan? This time for partial f partial y. So here's a more computational slogan. Partial f partial y, what that means is we differentiate with respect to y while fixing x. So for all intents and purposes, x is constant with a y derivative, with a partial y derivative, where y is constant with the partial f partial x derivative, with the x derivative. Okay? Here are the properties. Properties of partial differentiation. You can add them. You can pull out constants. There's a chain rule. Partial, if you differentiate a function of two variables, you know, there's a chain rule. There. Oh, I gotta put this away. Whoa. It is making me sick today. Sorry, I mostly wanted to show you guys those pictures on the projector because it's hard to, on a given day I may or may not be able to draw those worth anything, and I spent a fair amount of time trying to come up with those pictures carefully in the notes. So, oh no! Man. Fine. So again, definition. partial f, partial x at the point P is equal to d dx of f of, let's see here, P plus x hat, and then you put x equal to 0 at the end of that. Let me write it in a less weird notation. Partial f, partial x at the point, let's say x naught, y naught. What we do is we take the derivative with respect to time of the function evaluated at x naught plus time, and then y naught. Evaluate at t equals to 0, that's the partial derivative. So what's the difference with y? Partial f, partial y, what's the difference?
X is fixed. Is t.
Right, so I do f of x naught, comma, y naught plus t. Sometimes it's important to look at these in terms of the difference quotients. What would the difference quotient look like here? Limit as h goes to 0, f of x naught, comma, y naught plus h minus f of x naught, y naught, all divided by h. You can write the directional derivative straight up in terms of a difference quotient, limit of a difference quotient. It's important to be aware of that. But of course, we'd rather differentiate because that's our happy place, right? Computationally, differentiation is where it's at. So, how would I prove that partial x, partial y is equal to 0? How would I show that? Let me show you how. So what we do is we let f of xy equal to x. That's the function x, right? So if I write partial x, partial y, I'm thinking x of x is its own function, all right? So I'm really thinking of the function f where f of x comma y is equal to x, all right? So if I calculate partial x, partial y at the point x naught, y naught, what do I do? What do you guys want? I can go one of two ways here. Do you want me to do the differentiation or the limit of the difference quotient? Christina's pick.
I don't know. I'm still trying to figure out the difference between
Oh, these?
because it's the same as like x naught, y naught, but then the second one.
So the difference is this one has x varying, whereas that one has the y.
So you would be given that whole thing, right? Not just like partial differentiation of x naught, y naught.
That's well, this is the definition of the partial derivative. So
Sorry, keep going.
you're fine. So I'll tell you what, I'm going to use the limit. Limit as h goes to 0. And then I'm supposed to do f of what? F of x naught, comma, y naught plus h minus f of x naught, y naught, all divided by h. Okay, and then I just have to, what is the definition? Well, I mean, what's the definition of the function? What does it mean? What is f of x naught, comma, y naught plus h? Yeah. Right, but the definition of the function, so what is f of x naught, comma, y naught plus h equal to? Yeah, just x naught. How about the other one? Yeah, it's also x naught, yes. And so, there you have it, 0. To me, what this means is that x and y are independent variables. If I hold one fixed and vary the other, it can't tell. I mean, they're independent. if I let g of x comma y equals to y, and I calculate partial y in the same way, what happens? At the point x naught, y naught. Again, the difference quotient, I'm taking the partial derivative with respect to y, which means I just vary the y component holding x fixed. But g is the y function, right? So what does g do when I feed it the pair x naught comma y naught plus h? What comes down? Now h, you're doing some algebra there. So what you meant is y naught plus h minus y naught, right? Because I get y naught plus h from g of the pair, right? Because it just spits back out its y argument. And the other one just spits back out its y argument, which is y naught. They cancel. I'm left with what? H over h, which is, yeah, exactly. This simplifies to 1. But the point was arbitrary, right? The point is arbitrary. X naught, y naught, it's totally arbitrary. So it means that these identities we just worked out, they hold for all x and y in the plane. Okay? They hold for all x and y. So we have this little proposition, partial x, partial y is equal to 0, partial y, partial x is equal to 0, partial x is equal to 1, and partial y is equal to 1. I proved half of these. The other half very similarly proved. Now, tell you what, I'm going to lay off the proofs here for a second and do some examples. If we still have time at the end, I'll prove the other part of the proposition I just had up in the blue. I think it's worth our time to go through the chain rule and a couple of those other things. But let's work some examples. So, what if I have to partial differentiate x with respect to x, the expression xy squared? How does that work? The basic idea here is that y is not a function of x. So it's a constant in this differentiation, so I can pull it out. So this is really the same as partial x of x times y squared. And what's partial x? It's 1. Because this is 1. And any questions? Okay. Yeah.
What do you mean by them being independent so you can pull x separate?
Well, that's my point, is the definition is that a partial derivative with respect to x holds y fixed. So computationally what that means is if I have some expression with y, I can pull it outside the derivative.
Oh, you're pulling y outside of the derivative, not x.
Yeah. Here's another one. Partial x of sine of x squared plus y cubed. The chain rule we haven't proved yet, but we will, is this. Partial x of h of f of xy, generically speaking, is h prime of f of xy times partial h partial x. In other words, you differentiate the outside function and then you multiply by the derivative, the partial derivative. Here h is a function from the reals to the reals. So here my h is sine. So this is a chain rule. And so that chain rule put into practice here looks like this. It's cosine of x squared plus y cubed